Picture this. It's 1978, and a factory mechanic in Soviet Ukraine is standing in front of a room full of Porsche engineers in Stuttgart, explaining why their million-dollar cooling solution is garbage. He's wearing a threadbare jacket, speaking through a translator, and pointing at a diagram he drew on notebook paper. The Porsche guys are furious, embarrassed, and absolutely terrified. Because this nobody from behind the Iron Curtain just solved the problem they'd spent 5 years, and God knows how much money failing to fix. The cooling crisis of 1978. By the late 70s, air-cooled engines were dying, and everybody knew it. The writing was on the wall, carved in overheated aluminum and written in seized pistons. Porsche, the stubborn Germans who'd built their entire identity around air-cooled engines, were in crisis mode. The 911 was overheating in traffic, cooking itself in the Arizona desert, and generally behaving like a very expensive space heater on wheels. The problem was fundamental physics. Air cooling worked great when engines made 100 horsepower and ran at relatively low compressions. But by the 70s, emission regulations had forced compression ratios higher. Combustion temperatures were through the roof, and the simple act of blowing air over aluminum fins wasn't cutting it anymore. The 911 Turbo, introduced in 1975, was particularly catastrophic. That thing would heat soak so badly that Porsche had to put warning labels about touching the engine cover. Warning labels on a car that cost as much as a house. Detroit, meanwhile, was watching this with barely concealed glee. GM and Ford had gone water-cooled decades earlier and were convinced they'd made the right choice. Their engineers wrote papers about the superiority of liquid cooling, the thermal mass benefits, the precise temperature control. They had entire departments dedicated to cooling systems, radiators, thermostats, water pumps, hoses. It was complex, sure, but it worked. What nobody was talking about was efficiency. Water cooling added weight, complexity, and parasitic losses from the water pump. It solved the overheating problem by brute force, circulating coolant through a radiator big enough to cool a small building. It worked, but it was about as elegant as fixing a watch with a hammer. Porsche knew they needed something different. They'd tried everything. Bigger cooling fans, more aggressive fin designs, oil coolers the size of small radiators. They even experimented with liquid-cooled heads on air-cooled blocks, which was like putting a Band-Aid on a bullet wound. Nothing worked well enough. The 911 was going to have to go water-cooled, and for Porsche, that was like admitting defeat. Engineers at Weissach, Porsche's development center, were testing exotic solutions. Sodium-cooled valves like aircraft engines, phase change cooling systems, even some absolutely insane ideas involving refrigerant circuits. They had the budget, they had the engineering talent, they had the best equipment money could buy. What they didn't have was a solution that actually worked. Meanwhile, 5,000 miles east in the Soviet Union, a guy making 400 rubles a month was about to embarrass them all. Enter Vladimir Kozlov. Vladimir Kozlov was nobody special, which makes this story perfect. He was a factory mechanic at the ZAES plant in Zaporizhzhia, Ukraine, where they built the Zaporozhets, which was essentially the Soviet Union's answer to the Volkswagen Beetle, except worse in every measurable way. The Zaporozhets had a rear-mounted air-cooled engine that produced 40 horsepower on a good day and overheated if you looked at it wrong. Working conditions at ZAZ were, to put it mildly, challenging. This was the Soviet Union in the 70s. You didn't have unlimited budgets or fancy equipment. You had what you had, and you made it work, or you went home. Parts were scarce. Technical literature from the West was nearly impossible to get. If something broke, you couldn't just order a replacement from a catalog. You fabricated it, you adapted something else, or you did without. Kozlov had been dealing with overheating Zaporozhets engines his entire career. The official solution from ZAZ Engineering was to tell drivers not to use their cars in summer traffic. Seriously. That was the official recommendation. Don't drive your car when it's hot out. Brilliant engineering, comrades. But Kozlov had a problem. He was also an amateur racer, and in Soviet racing circles, the Zaporozhets was actually competitive in its class, mainly because it was light and everybody was running essentially the same equipment. The problem was that engines would overheat after about 10 laps, and either seize or lose so much power that you might as well park it. He couldn't just buy a better engine. This was the USSR. You ran what you had. He couldn't import parts from West Germany. He couldn't even get decent bearings half the time. What he could do was think and experiment and try things that made no sense according to conventional engineering wisdom. The breakthrough came from an unlikely source. Kozlov had been reading a technical paper about industrial machining, specifically about using oil mist for cooling cutting tools. The concept was simple. Atomized oil, suspended in air, had incredible heat transfer properties because of the massive surface area of the tiny droplets. Why? Machine shops were using it to cool drill bits and lathe tools because it worked better than flood cooling with straight oil. Kozlov had what can only be described as a crazy idea. What if you could apply the same principle to engine cooling, not spraying oil on the outside of the engine, but introducing an oil mist into the cooling airstream? The oil droplets would absorb heat, the air would carry it away, and the oil would eventually condense and drain back to the sump. His colleagues thought he'd lost his mind. You can't just spray oil into your cooling system. It'll carbonize, it'll clog everything, it'll catch fire. Every engineer he talked to had a reason why it wouldn't work. Kozlov built it anyway. The radical solution. Here's what Kozlov actually did, and pay attention because this is where it gets brilliant. He took a Zaporozhet's cooling fan shroud and modified it with a series of tiny nozzles, basically repurposed fuel injector nozzles he'd scrounged from a diesel truck. These nozzles were fed from a small pressurized oil reservoir. It's self-fed by a simple mechanical pump driven off the engine's existing oil pump circuit. The nozzles created an ultra-fine oil mist. We're talking droplets measured in microns that mixed with the cooling air before it hit the cylinder fins. The oil mist would impact the hot aluminum, instantly vaporize and absorb massive amounts of heat, then condense back into liquid oil that drained into collection channels Kozlov had machined into the fan shroud. From there, it gravity-fed back to the oil sump. The entire system added maybe 2 kilograms to the engine. 2 kilograms. Compare that to a water cooling system, with radiator, hoses, water pump, thermostat, and coolant, which added something like 25 to 30 kilograms to a typical small engine. Why this worked is actually fascinating from a thermodynamics perspective. When oil vaporizes, it absorbs heat. A lot of heat. The latent heat of vaporization for oil is significantly higher than for water at the same temperature. But here's the clever part. Unlike water, oil doesn't boil at a fixed temperature. The light fractions vaporize first, cooling the engine, while the heavier fractions remain liquid and continue to lubricate. This created a self-regulating system. When the engine was cool, not much oil vaporized, so you didn't waste it. When the engine got hot, more oil vaporized, providing more cooling exactly when you needed it. There was no thermostat, no temperature sensor, no control system. It was purely mechanical and worked on basic physics. The oil mist also did something unexpected. It created a microscopic oil film on the cylinder fins, which actually improved heat transfer from the aluminum to the air. This was completely accidental, but it meant that even the air cooling component worked better than stock. Kozlov tested it first on his own Zaporozhets. The results were immediate and dramatic. Engine temperatures dropped by 35 degrees Celsius under the same conditions that would normally cause overheating. That's 63 degrees Fahrenheit for the Americans in the audience. On a 40 horsepower engine, making maybe 90 degrees Celsius at the cylinder heads, dropping it to 55 degrees was transformative. But here's where it gets really interesting. With the lower temperatures, Kozlov could advance the timing without detonation. More timing meant more power. He could also lean out the mixture without overheating the exhaust valves. Leaner mixture meant better fuel economy and more power. The cooling system modification resulted in a 47 horsepower engine, a 17% increase with better reliability and lower oil consumption, 17% more power from a cooling modification. Let that sink in. The engineering genius. Spa. Nobody saw. The brilliance of Kozlov's system wasn't just that it worked. It was how elegantly it solved multiple problems simultaneously while creating almost no new problems. Compare this to conventional liquid cooling, which solves overheating but creates complexity, weight, failure points, and parasitic losses. The oil mist system had no water pump stealing power. A water pump on a small engine typically consumes 2 to 3 horsepower. That's 5 to 7% of the total output on a 40 horsepower engine. Kozlov's system used a tiny fraction of that power because the oil pump was microscopic, and the pressure requirements were minimal. There was no radiator to get damaged or leak, no hoses to crack, no coolant to change, no antifreeze to worry about in winter. In the Soviet Union, where winter temperatures could hit -40 Celsius, this was huge. Liquid cooling systems would freeze solid overnight. Kozlov's system used engine oil, which was designed to function in extreme temperatures. The system also provided additional lubrication to the cylinder walls. The oil mist would eventually condense and find its way into the combustion chamber in microscopic quantities, providing extra lubrication to the rings and cylinder walls. Oil consumption actually decreased because the engine ran cooler and the rings sealed better. Component count was absurdly low. The entire system consisted of a modified fan shroud, 6 nozzles, a small oil reservoir, a simple mechanical pump, and some drain channels. That's it. No electronics, no sensors, no complex control systems. A village mechanic could fabricate the entire thing with basic machine tools. Cost was equally absurd. Kozlov estimated his entire system cost about 40 rubles in materials, which in 1978 was maybe $60 US. Compare that to Porsche's exotic cooling experiments, which were burning through millions of Deutsche Marks with nothing to show for it. The system scaled beautifully too. Kozlov tested it on larger engines and found that the principle worked just as well. You just needed more nozzles and slightly higher oil pressure. The fundamental concept remained the same. From a maintenance perspective, it was brilliant. The only thing that could fail was a nozzle getting clogged, and even then, the engine would just run slightly hotter, but wouldn't catastrophically overheat. There were no catastrophic failure modes. A burst radiator hose will destroy an engine in minutes. A clogged oil mist nozzle would just reduce cooling efficiency slightly. The temperature control was also more precise than liquid cooling. Water cooling systems have thermal mass. The coolant takes time to heat up and cool down, creating temperature cycling. Kozlov's oil mist system responded instantly to heat load changes because there was minimal thermal mass in the system. The engine temperature remained stable under varying conditions. Engineers today would call this a phase change cooling system, and they'd be right. But Kozlov didn't have that terminology. He just knew that when oil vaporized, it got cold, and cold was what he needed. Word spreads to Porsche. The Soviet racing scene in the late 70s was surprisingly competitive, even if nobody in the West paid attention to it. There were amateur racing clubs, hill climbs, autocross events, all conducted with whatever cars people could get running. The Zaporozhets racing class was particularly active because the cars were cheap and available. When Kozlov started winning everything, people noticed. His engine ran cool, never lost power, and was clearly making more horsepower than the competition. Other racers wanted to know his secret. The Soviet automotive press, such as it was, ran an article about the mysterious Zaporizhzhia mechanic who had solved the overheating problem that Zaz engineers had declared unsolvable. This is where things get interesting from a Cold War espionage perspective. Western intelligence agencies, particularly the CIA and West German BND, maintained extensive operations to acquire Soviet technical information. They were mainly looking for military technology, but automotive innovations were also monitored because dual-use applications were common. A technical attaché at the West German embassy in Moscow happened to read the Soviet Automotive magazine article about Kozlov. He was a car guy, happened to be interested in cooling systems, and filed a report back to Bonn that eventually made its way to Stuttgart and landed on a desk at Porsche. Porsche's initial reaction was dismissive. Oil mist cooling sounds messy, complicated, and probably didn't work as well as the article claimed. Soviet propaganda was notorious for exaggerating technical achievements. They ignored it. But one engineer, Hans Schmidt, nobody important, just a cooling system specialist, was intrigued. He'd been banging his head against the 9/11 cooling problem for 3 years and was desperate enough to consider anything. He wrote a memo suggesting they investigate further. His superiors said no. They weren't going to waste resources chasing some Soviet mechanic's backyard experiment. They had real engineering to do with real budgets and real equipment. Schmidt did something that engineers aren't supposed to do. He went rogue. He built Kozlov's system on his personal 911, on his own time, with his own money. This was 1979. He fabricated the nozzles, machined the oil reservoir, modified his fan shroud, and installed the whole system in his garage. The first test drive was on the Autobahn on a hot summer day. Schmidt later told colleagues that he drove from Stuttgart to Munich and back, flat out most of the way, in traffic. And the engine temperature never spiked. Never. His bone-stock 911 would heat soak in 20 minutes of hard driving. With the oil mist system, it ran cool all day. He brought the car to work and showed his colleagues. They were stunned. They instrumented the engine, ran it on dynos, measured everything they could think of. The oil mist system worked exactly as Kozlov's paper had described, better even. On a 911 engine, which made significantly more heat than a Zaporozhet's, the cooling effect was even more pronounced. Porsche management suddenly became very interested in the Soviet mechanic. Detroit's spectacular missus. Here's where the story gets frustrating. Porsche wasn't the only company that learned about Kozlov's system. General Motors and Ford both had intelligence operations that monitored Soviet technical developments. They both received reports about the oil mist cooling system. They both dismissed it. Internal memos from GM's engineering division, obtained through FOIA requests years later, show that multiple engineers recommended investigating Kozlov's system. And management response was consistent, not a priority. Liquid cooling is the proven solution. Soviet technology is generally inferior to Western standards. The arrogance is breathtaking. Here was a system that solved multiple problems simultaneously. Cost almost nothing, weighed almost nothing, and actually worked better than liquid cooling in many applications. And Detroit said no thanks, because it came from a Soviet mechanic. Ford's response was even worse. One engineer wrote a detailed memo explaining the thermodynamic advantages of phase change cooling and specifically recommended funding a research program into oil mist systems. His supervisor wrote back, "If this was viable, we would have thought of it already." Read that again. "If this was viable, we would have thought of it already." That single sentence encapsulates everything wrong with Detroit's engineering culture in the late 70s. The assumption that good ideas could only come from within, that outsiders, especially Soviet outsiders, couldn't possibly know something they didn't. This was the same thinking that let the Japanese eat Detroit's lunch in the small car market. The same thinking that dismissed front-wheel drive as a gimmick. The same thinking that said fuel economy didn't matter until gas hit $5 a gallon. The cost of this arrogance is hard to calculate, but consider this. Every air-cooled engine application, from the late 70s through the 90s, could have potentially benefited from oil mist cooling. Motorcycles, small aircraft, generators, industrial equipment, racing engines. We're talking about millions of engines worldwide. The potential fuel savings alone would have been enormous. Lower operating temperatures mean better efficiency. Kozlov's system showed 7 to 10% better fuel economy on the same engine. Apply that across millions of vehicles over decades, and you're talking about billions of gallons of gasoline saved. But Detroit said no. Not because the technology didn't work, not because it was too expensive, but because it was invented by the wrong person in the wrong place. The results that broke physics. Let's talk about what Kozlov's system actually achieved, because the numbers are almost unbelievable. On the Zaporozhet's 40 horsepower engine, cylinder head temperatures dropped from 90 Celsius to 55 Celsius under full load conditions. That's a 35-degree reduction, which in engineering terms is massive. Oil temperature, measured at the sump, actually decreased. This was counterintuitive because the system was using oil as the cooling medium. How could oil temperature go down when you're using it to cool the engine? The answer is that the vaporization process cooled the oil more effectively than the traditional air oil cooler. The oil that drained back to the sump had been cooled by its own vaporization cycle. Power increased by 17%, as mentioned earlier, but here's what's remarkable. That power increase came with improved reliability. The engine could sustain full power output indefinitely without distress. Stock Zaporozhet's engines would overheat after 15 to 20 minutes of full throttle operation. Kozlov's modified engines could run at redline for hours. Oil consumption decreased by approximately 30%. Lower operating temperatures meant better ring seal and less oil burning. The microscopic oil mist that entered the combustion chamber actually improved lubrication without significantly increasing consumption. Fuel economy improved by 8 to 10%. Cooler combustion chambers allowed leaner mixtures and more advanced timing without detonation. This translated directly to better fuel economy and cleaner combustion. The system added 2 kilograms to the engine weight versus approximately 28 kilograms. For an equivalent liquid cooling system, that's a 26 kilogram weight savings, which on an 800 kilogram car is over 3% of the total vehicle weight. Parts count for the entire system, 32 components. Parts count for an equivalent liquid cooling system, over 200 components. Fewer parts meant fewer failure points and lower manufacturing costs. Maintenance requirements: check oil level, clean nozzles annually. Compare that to liquid cooling: flush coolant, replace hoses, check water pump, test thermostat, pressure test system, maintain radiator. The oil mist system was dramatically simpler. Racing results speak for themselves. Kozlov's Zaporozhets dominated Soviet amateur racing from 1979 through 1982. Other competitors started copying his system, often unsuccessfully because they didn't understand the critical details about droplet size and oil pressure. Porsche's testing on the 911 showed similar results, scaled up appropriately. A 911 Turbo with oil mist cooling showed a 22-degree reduction in cylinder head temperatures, eliminated heat soak issues, and allowed sustained boost pressures that would destroy a stock engine within minutes. The system worked. It worked better than conventional cooling. It was simpler, lighter, cheaper, and more reliable. Every objective measure said that this was superior technology. So why are you reading about it in a YouTube script instead of seeing it on every air-cooled engine built in the last 40 years? Why it died anyway. The death of Kozlov's innovation is a story of bad timing and geopolitical chaos. Just as Western companies were starting to take the oil mist cooling system seriously, the Soviet Union began its terminal collapse. By the mid-80s, the USSR was in economic freefall. The ZAZ factory where Kozlov worked was struggling to maintain basic production, let alone support innovative research. Kozlov himself had become somewhat of a celebrity in Soviet automotive circles, but this brought problems. The Communist Party didn't like individuals getting too much attention or credit. They preferred collective achievements attributed to the wisdom of the party. Kozlov found himself increasingly marginalized. His work criticized as individualistic and contrary to socialist principles. By 1986, he'd left ZAZ and was working as a private mechanic, which in the Soviet system meant operating in a legal gray area. His documentation of the oil mist system, his test data, his engineering drawings, all of it remained property of the ZAZ factory and was effectively inaccessible. When the Soviet Union collapsed in 1991, the ZAZ factory privatized chaotically. Records were lost, destroyed, or simply abandoned. Kozlov's technical papers, his test data, his detailed engineering drawings, most of it disappeared during the transition. What survived was scattered and incomplete. Meanwhile, Western automotive companies had moved on. The late 80s and early 90s saw massive advances in liquid cooling technology, electronic thermostats, variable speed electric cooling fans, aluminum radiators, long-life coolants. Liquid cooling was getting better, lighter, and more reliable. More critically, air-cooled engines themselves were dying out. Porsche finally capitulated and made the 996 their first water-cooled 911 in 1998. Volkswagen had already gone water-cooled with the Golf. Motorcycle manufacturers were moving to liquid cooling for emissions reasons. The market for air-cooled engines was shrinking. But here's the real tragedy. The specific application where oil mist cooling would be most valuable, high-performance racing engines and small aircraft, never got to properly evaluate it. The technology disappeared behind the Iron Curtain before it could be fully developed and commercialized. Kozlov died in 2004, relatively unknown outside a small circle of Soviet-era racing enthusiasts. His obituary in a Ukrainian automotive magazine mentioned his cooling system innovation, but described it as a curious experiment rather than the genuine engineering breakthrough it was. The legacy and modern rediscovery. The story should end there, a forgotten innovation lost to history. But in 2015, a mechanical engineering graduate student at Moscow State University named Dmitry Volkov was researching Soviet-era automotive innovations for his thesis. He found a reference to Kozlov's system in an old racing magazine and became obsessed. Volkov tracked down surviving racers who'd known Kozlov, found fragmented documentation in the factory archives, and eventually reconstructed the oil mist cooling system from incomplete information and educated guesses. He built it, tested it, and published his results in an obscure Russian engineering journal. That paper caught the attention of several Western engineers working on hybrid vehicle thermal management. They realized that Kozlov's principle could be applied to cooling electric motors and power electronics, where weight and complexity are critical concerns. A German startup called Thermomist, founded in 2018, commercialized a modern version of Kozlov's system for electric motor cooling. They use a synthetic oil mist to cool high-performance electric motors in racing applications. The system weighs 60% less than liquid cooling and provides better thermal management under transient loads. Formula E racing teams have reportedly tested oil mist cooling systems, though details remain confidential due to competitive secrecy. The weight savings alone would be worth several tenths per lap on a typical Formula E circuit. General aviation has shown renewed interest in oil mist cooling for air-cooled aircraft engines. Lycoming and Continental, the two major manufacturers, have both conducted research into phase change cooling systems. No commercial applications yet, but the research continues. The irony is delicious. The technology Detroit dismissed in 1979 as Soviet nonsense is now being explored by cutting-edge startups and Formula E teams. The innovation Porsche briefly tested and then abandoned is finding new applications in the electric vehicles. Kozlov's backyard experiment has become relevant again, 4 decades later, in a completely different context. The philosophy of outsider innovation. The Kozlov story is really about how innovation happens and where it comes from. It's a perfect example of how constraints breed creativity, how outsiders see solutions insiders miss, and how establishment thinking kills good ideas. Kozlov succeeded precisely because he didn't have access to unlimited resources. He couldn't just throw money at the problem. He couldn't order exotic materials or complex control systems. He had to think creatively with limited means. That constraint forced elegant simplicity. Porsche's engineers, with their million-dollar budgets and advanced facilities, were trying to solve the cooling problem with complexity. Exotic materials, sophisticated control systems, computer modeling. They were adding complications to solve complications. Kozlov subtracted complications. Detroit's engineers didn't even try because they'd already decided they knew the answer. Water cooling worked. Why look for alternatives? This is the engineering equivalent of, we've always done it this way. It's the death of innovation. The lesson here transcends automotive engineering. How many good ideas get dismissed because they come from the wrong person or the wrong place? How many innovations die because established companies can't imagine that an outsider might know something they don't? Think about this. Kozlov was a factory mechanic making 400 rubles a month in Soviet Ukraine. No engineering degree from a prestigious university. No published papers, no industry connections. By every conventional measure, he was nobody qualified to revolutionize engine cooling. And yet, he did exactly that. He solved a problem that Porsche's best engineers, with unlimited budgets and the latest technology, couldn't solve. He did it with notebook paper, scavenged parts, and pure creative thinking. The story reminds us that innovation doesn't require permission. It doesn't require credentials or budgets or fancy equipment. It requires curiosity, persistence, and the courage to try things that conventional wisdom says won't work. Every time a major company dismisses an idea because it wasn't invented internally, they risk missing the next Kozlov. Every time an engineer says, if it was possible, we would have thought of it already, they reveal their blindness to possibility. The most valuable innovations often come from the margins, from people working with constraints, from outsiders who don't know what's supposed to be impossible. Kozlov didn't know his oil mist system wasn't supposed to work. He just built it and tested it and proved that it did. So, here's my challenge to you. What impossible problem are you working on? What constraint is forcing you to think creatively? What established wisdom are you willing to question? The next revolutionary innovation might not come from a billion-dollar R&D lab. It might come from your garage, your workshop, your notebook. It might come from you, working with whatever you have, trying things that aren't supposed to work. Kozlov proved that genius plus garage beats billions plus bureaucracy. He proved that one person with a crazy idea and the determination to test it can outsmart entire industries. He proved that the establishment doesn't own innovation, even if they think they do. That's the real legacy of Vladimir Kozlov's oil mist cooling system. Not the technical achievement itself, impressive as it was, but the reminder that innovation belongs to whoever's brave enough to attempt it, regardless of credentials, resources, or establishment approval. The next time someone tells you your idea won't work, remember the Soviet mechanic who embarrassed Porsche with notebook paper and scavenged parts. Remember that the establishment is often wrong, especially when they're absolutely certain they're right. And maybe, just maybe, build the thing anyway. Because sometimes the best ideas are the ones nobody else believes in until you prove them wrong.